everyone, welcome to another session of solid state. In this session I will be explaining you about imperfections in solid. Okay. See? Imperfections in solids. Okay, so basically there are types of defects. One is point defect. So point defect are the irregularities, okay, or deviations from ideal arrangement around a point, okay, or a atom in a crystal substance. For example, if you remember in previous session I explained you about one sphere, two sphere, three sphere, that was arrangement in a two-dimensional one-dimensional plane. So if you see, there were one sphere, two sphere, three sphere. So if a point is misplaced, or let's say if a point is substituted by something else, that give rise to your point defect. Okay, whereas line defect are irregularities or deviations from ideal arrangement in the entire rows of lattice point. So let's say that if you are looking at the two-dimensional arrangement, let's say one at a row of atom is like this, another row below, another row below, next row is below it. So if one line is showing some irregularity, or it is kind of entirely replaced by something else, that give rise to your line defect. Okay, both of these defects are, since irregularities in crystals, we also call them crystal defects. Okay, now the focus will be only on point defects. So point defects are of three types. One is stoichiometric defect, second is impurity defect, and the third one is non-stoichiometric defect. Okay, so let's go a little bit more in detail about stoichiometric defects. Now, first type of stoichiometric defect is vacancy defect. As the name suggests, okay, some of the sites are vacant, okay, like maybe vacant. So basically, if you see, this is the original lattice, 1, 2, 3, 4, all the spheres are there, but this sphere here is missing, as well as this sphere here is missing. So if you see, this is having the same volume as before, but the mass is going to be reduced. Hence, this defect, vacancy defect, give results in the decrease in density of the substance, because mass is decreasing. Density is what? Mass by volume. If mass is reducing, your density decreases. Okay, and it develops usually when the substance is heated. Okay, next type of defect is interstitial defect. Interstitial defect is when some constituent particles, that can be atoms, ions, or molecules, occupy an interstitial site. Now, this is the original structure: one sphere, two sphere, three sphere, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are the original structure. If you see that this sphere is extra, this here is extra. So this spheres are occupying the interstitial sites. Basically, this open space here is your interstitial site, same as this one, same as this one. So some atoms or ions are occupying this interstitial site. Since more number of atoms are present in a given volume, the density of the substance increases. Okay, so this is your interstitial defect. Now, this is in case of covalent bonds or like non-ionic substances. For ionic substances, we know that they should maintain electrical neutrality. Basically, the number of positive charge should be equals to number of negative charge. So for this, we do not study as simple vacancy or interstitial defect. We study Frankel and Schottky defects. Let's go into ionic defects. So one type of defect is Frankel defect. So Frankel defect is also known as dislocation defect. Okay, that's another name for Frankel defect. What happens in this case? The smaller ion, usually it's a cation, because cations are losing electrons, and the size of cation is always very small as compared to anion. So is dislocated from its natural site, and it occupies an interstitial site. If you see here that in this structure, I see that positive charge here is missing. Okay, so that is your missing. Okay, that's a vacancy, but this positive charge occupies this site here, that is your interstitial site. Okay, so basically it creates vacancy at this point, and it creates an interstitial defect at this point. Okay, so it creates a vacancy defect at its original site and interstitial defect at its new location. Okay, important here is that this does not change the density of the solid. Okay, and it arises where a large difference in size of ions is present. Example: ZnS, AgCl, AgBr, AgI, due to the small size of cations. Okay, so just focus on AgBr because this is an important part here. Now, next is Schottky defect. So Schottky defect is basically a vacancy defect in ionic solid. Okay, so basically if you see, this is missing, that is a positive charge is missing here, a negative charge is missing. Okay, here also we see a positive charge is missing, a negative charge is missing. So this happens because it has to maintain its electrical neutrality. So if two positive charges are missing, two negative charges should be missing, that is two anions, so two cations should be missing. Now this defect, Schottky defect, decreases the density of the substance. Okay, so this happens when cation and anion are almost of similar size. Example: NaCl, KCl, CSCl and AgBr. I told you to focus on AgBr because AgBr can show Schottky defect as well as Frankel defect. Okay, Frankel defect, AgBr. That's why I told you to focus on AgBr. So if you want to remember one example, AgBr is the best because you can write it on both. Okay. Now, next is impurity defect. Impurity defect, as the name suggests, there is some impurity. Okay, let's say that here we have a structure and it was already molten NaCl. So if you crystallize molten NaCl which contained little amount of SrCl2, okay, what will happen? Some of the sites of Na plus will be occupied by Sr2 plus. So each Sr2 plus will replace two Na plus ions. Reason for this is again to maintain electrical neutrality. So the positive charge on this is +2 and positive charge on one Na plus will be +1. So if two are replaced, then the charges are balanced. So what happens is, let's say that this is NaCl, 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 Sr. So instead of Na, I am getting Sr2 plus. So if you see, there is an vacancy here. Okay, that is because two of the Na plus will be replaced by one Sr2 plus. Okay, so this is the scenario that you get. So one remains vacant. This site is remaining vacant. The cationic vacancies thus produced are equal number of Sr2 plus. So how many Sr2 plus are present? That many vacancies will be present. Okay. Another example of this situation can be CdCl2 and AgCl. So this was about impurity defect. Next is the non-stoichiometric defect. Non-stoichiometric defect means that we cannot comment on the number of cations and anions that are showing this defect. Now, first type is metal excess defect. So here the metal is present in larger quantity. That's why metal excess defect. Okay. So this can happen. First case is due to anionic vacancy. Anionic vacancy meaning the anion is missing. So if you see here, this is missing. Let's say that this is your NaCl example, or you can say KCl example. So your Cl is missing and an electron is occupying its site. So what happens? Like when you heat the crystal of Na, okay, when the crystals of NaCl are heated in atmosphere of sodium vapor, so this Cl diffuses to the surface and crystallizes, combines with Na atoms to give NaCl. So this happens by loss of an electron, and that electron occupies this site. Okay. So this site is also known as F center. It's an anionic site occupied by unpaired electron. So that is F center. Okay. So this is responsible for imparting yellow color to the crystal of NaCl. About coloring, we will study much more in detail in coordinate compounds. Okay. And apart from this, like excess of lithium gives LiCl pink color, and excess of potassium gives KCl violet or lilac color. So that is responsible for color or specific color. These colors are important. Okay, so please remember that NaCl is yellow in color, and when excess of lithium is there, it is pink in color in LiCl. Excess of potassium gives violet or lilac color in KCl crystal. Okay, so this was, remember, due to anionic vacancy. Basically anions are in less quantity. Another reason for metal excess can be due to presence of extra cations at interstitial site. Okay, here below is an example that when zinc oxide, which is white in color at room temperature, on heating it loses oxygen and turns yellow. So this is a property. Now, why on heating it loses oxygen and turns yellow? This is the reaction. What happens is ZnO when heated loses oxygen. Now there is Zn2 plus and two electrons. Now this Zn2 plus goes back inside the crystal and occupies an interstitial site, and electrons also stay nearby in other positions like nearby. So excess of Zn2 plus ions move into the interstitial site and electrons to the neighboring interstitial site. So this is responsible, that Zn2 plus and these electrons are responsible for imparting a yellow color. So please remember that zinc oxide ZnO, when you heat it loses oxygen and turns yellow. It's a property. Okay, so this is another type of metal excess defect. Here it is because the extra cation is occupying the interstitial site. So that's why metal is present in larger quantity, hence metal excess defect. Next is metal deficiency defect. Now, how can be metal be present in deficiency? For example, consider a case of FeO. Okay. Now, FeO, the oxidation state of Fe is +2 and oxygen is -2. Okay. So what happens? Let's say some of the Fe2 plus are replaced by Fe3 plus. So what will happen, to in order to maintain the neutrality, less iron are required as compared to oxygen. Okay, so we get a composition, for example, Fe 0.950. Okay, the range may actually be from Fe 0.930 to 0.960, but on average we are writing like this. Okay, so this is happening because some of the Fe2 plus ions are missing, and the loss of the positive charge is made up by presence of required number of Fe3 plus ion. Okay, so that's it for this part. Okay, thank you all for listening to this. I hope you all enjoyed. Thank you.